Welcome to example number 5. We have a sample gas containing 1,000 moles of nearly ideal monatomic gas, and it's put through a series of processes. In process AB, this is an isochoric process, BC is an isothermal process, and C to A is an isobaric process. So let's start off with part A. We asked to find the temperature at state A and the temperature at B, and then also to find the volume at point C. So since it's an ideal gas, we can use the ideal gas law, which is PV equals nRT, and solve for the temperature at A, which is the pressure at A, times the volume at A, divided by the number of moles in the gas constant. Now the pressure at A is in atmospheres. That's not very good because the reason is, as you see, as you put in 1,000 moles down below, and then the gas constant, which is 8.314 joules per mole Kelvin, we need to make sure that our units of pressure are going to cancel out with all the other units. We need to make sure pressure is in pascals, or newtons per meter squared, so that when we have everything multiply out, we're going to get an answer that is just going to be in Kelvin. So we're going to need to change that 1 atmosphere into pascals. We're going to have to multiply by 1.013 times 10 to the power of 5 pascals for every atmosphere. And then we also have a volume of 22.4 meters cubed. This is already kept in the appropriate units. So be careful with your assignments. You're going to have sometimes questions that are going to be given to you in liters. You'll have to change that to meters cubed, or you'll be given questions that are given in atmospheres, and you'll have to change it to pascals. Typically on the AP exam, they like to give it to you in the right unit, so you don't have to worry about the unit conversion. And when you multiply all this out, you're going to get around, or should be, 273 Kelvin, which is basically 0 Celsius. Hopefully this makes sense. And we just started this at a STP, standard temperature and pressure, and volume. So now moving on to part B of this temperature, at point B actually, we want to find that. Now you could go back and use the ideal gas law. Use the same equation we did before, but use pressure B, volume B, and moles in R. Or alternatively, you can say, well, since the volume is constant, then the pressure is directly proportional to the temperature. So as we move from pressure A is really half of pressure B, thus we can see that temperature at B will be twice the temperature at A. So that will be 2 times 273 Kelvin, which gives you a temperature of 546 Kelvin. Then next we have the temperature at C. Hopefully you realize that it'll be the same as the temperature of B, which we've just established as 546 Kelvin. So as you go along process B to C, this is an isothermal process, hence the temperatures are the same, and therefore the product of the pressure times the volume is constant in this case. So pressure is inversely proportional to volume, or pressure at B times the volume at B is the same as the pressure at C times the volume at C. Now the pressure at C, if you look at it, the pressure at C is half the pressure at B. It's reduced from 2 atmospheres down to 1 atmosphere. So now we have pressure B times volume of B equals half of pressure at B times the volume at C. And so the pressures cancel out now, and we'll find out that the volume at C is twice the volume at B, which is 2 times 22.4 meters cubed, which gives you 44.8 meters cubed. Now let's go on to part B, which is finding the work done over each process. So along process A to B, so we'll call that work A to B here, we have an isochoric process, and you can see there's a vertical line. Remember that the work done is the area under the PV curve. In this case, there is no area under this curve because it's vertical. So that work done is easy, it's 0. Next, we're going to calculate the work done from B to C. Now, in this on the AP exam, I would not expect you to do because it involves calculus. But let's go back to the notes and see if you can find that equation to calculate the work done over an isothermal process. Take a look back at the notes. Aha, there it is, right here. And we're going to be using this formula, which involves a natural logarithm. So the work done from B to C along this isothermal process is negative nRT, the natural logarithm of the final volume, so that's volume C, divided by the volume at initially, which is point B. And then substituting in, we have 1,000 moles, the gas constant, the temperature of 546 along at B and C, and then our volume ratio is 2 to 1. We're going to get a work done is negative 3.1465 times 10 to the power of 6 joules. And this value represents the area under this curve. And there it is right there. Now we're going to calculate the work done from C to A, which is the area under the curve from here all the way down to the axis. And there's the area, so really we're finding the area of this rectangle. So to find that area, the work done from C to A is simply negative the pressure at that location multiplied by the change in volume. So the change pressure here at A is the same as the pressure at C, and that was 1.013 times 10 to the power of 5 pascals. And the volume is decreasing, so it's going to be a negative change in volume from 44.8 to 22.4, so that's a negative 22.4 meters cubed. And that will give you a work of positive 2.26912 times 10 to the power 6 joules. In the last part, we're asked to calculate the total work done during the whole cycle. Hopefully you realize that during a closed cycle, it is really the area that is enclosed. And that area represents the total sum of all of the works done. So if you take work AB and work BC, and work C to A, then that would be equal to the total net work done. And there are all the works here, and when you add that all up, you'll get negative 8,000, well, it looks like 877,383 joules. Or you can round this off to about negative 880,000 joules, or negative 880 kilojoules. Now you'll notice the answer is negative because the gas is doing work on the surroundings, and hence this is really indicative of it being an engine. An engine is a process where the cycle goes in this clockwise fashion. If it goes counterclockwise, then it's a refrigerator. And that's it for this example.